This is a video lesson for free body diagrams. In this video, we're going to learn what free body diagrams are, how to draw them, and how to use them to determine the net force on an object. All right, let's talk about free body diagrams and how to draw them. So first, a free body diagram is a tool that physicists and engineers use to figure out what the net force acting on an object is, which we can then use to determine things like acceleration on the object, or if we know the acceleration, we can figure out what the forces are acting on the object are. It's a very powerful tool, and we use it all the time in physics. So let's look at the steps on how to draw a free body diagram. So the first step is to start with a dot representing the center of mass of the object. Second step, draw a box around the dot, and this is optional. You'll sometimes see free body diagrams with boxes. Sometimes you'll see free body diagrams without them. I like to draw the box because it gives you a little bit more context. Step number 3, draw arrows from the box representing the forces interacting with the object. So let's say that the object is moving to the right and that there's a force opposing that motion. And then there's a gravitational force moving downward and an upward force opposing that gravitational force. So A, the longer the arrow, the stronger the force. And B, the arrows should be in the same direction as the forces, because remember that forces are vectors. So here, the arrows are drawn in the direction that the forces are pointing. So we have this arrow to the right, which is in the direction that the force is pushing. We have the arrow to the left, and so on. Okay, number 4, label the arrows with which forces they represent. So we have, this is Fg for gravity. This is Fn, this is the normal force. So if the box is on the ground, or whatever the object is, if it's on the ground, we have a gravitational force pulling it down, and we have the normal force opposing that force. Then we have, let's call this an applied force. And then we have, we'll say this is the friction force. Okay. And then finally, step 5, we want to determine the net forces acting on the object. So we look at our sum of forces in the y direction. We have Fn is up, so that's positive, minus Fg. Those are equal to each other, so that's 0. And then we have the sum of forces in the x direction. So we have applied force minus frictional force, and the applied force is greater, so our sum of forces in the x direction is to the right. All right, so we have an example here. So the cabin of a small freight elevator is secured to the motor by a cable. So that means we're going to have a tension force. It's moving upward while slowing down. There's no contact between the cabin and the elevator. Ignore air resistance. Okay, so first thing we're going to do is do a little circle in the middle with a box around it. Okay, so we always have gravity. So we'll draw gravity first. And we'll go ahead and label that as F sub g. Then the box is moving up, the elevator is moving upward, but it's slowing down, which means it's an unbalanced force, which means that the gravitational force is stronger than the tension force. The tension force, remember we have tension because it's a cable. All right, we don't have any forces on the sides because it's not touching the cabin. The cabin is not touching the elevator shaft. If we were touching the shaft, then we would have normal forces over here. Okay, So if we wanted to do our sum of forces, we don't have any force in the x direction, so we'll skip those. So we just have sum of forces in the y direction. We have Ft minus Fg, and that's equal to downward. So the greater force is downward in this example. So even though the elevator is moving up, the gravitational force is stronger. So the sum of forces are downward. Okay, let's look at this example. So Ethan is dragging a bag of grass to the right from the garage to the street on the evening before garbage pickup day. Draw a free body diagram to determine the net force acting upon the bag. Okay, we have these forces listed. We have the gravitational force, which is sometimes written mg, which we'll get into at some point, equals the normal force, which is 56 newtons, applied force, which is 44 newtons, and the frictional force, which is 29.5 newtons. So we'll start with our free body diagram here. All right, so we have our gravitational force, F equals Fmg, which is equal to 56 newtons. And the normal force, which is also 56 newtons. We have our applied force, just dragging it to the right. And that is 44 newtons. Then we have a frictional force, which is opposing the motion, so it's to the left, of 29.5 newtons. All right, so now we want to do our sum of forces. So we'll do sum of forces in the y direction. So we have upwards is positive, so we have 56.0 newtons minus 56.0 newtons, which equals 0 newtons. Then we have in the x direction, we have to the right is positive, so we'll do 44.0 newtons minus 29.5 newtons, and that gives us a net force in the x direction of 5. That gives us a net force 14.5 newtons. All right, and there's our net force. 14.5 newtons, and that's positive, so it's in the rightward direction. All right, example number 2. Unfortunately for Vanessa, the wheels on her suitcase are not working. She pulls on the strap in an effort to budge it from rest and drag it to the curbside check-in desk to the left. All right, and here's our list of forces. So we have our gravitational force, or that's really the weight of the object, the weight of the suitcase. So mass times gravitational force is the weight. And then offset, and that's the normal force. So those two are equal, 272 newtons. And then the tension force, so she's pulling on the strap, and that's it. So the strap, so that's the tension force. And then offset or opposed by the frictional force. Okay, so let's go ahead and draw our free body diagram. So we have gravitational force. So Fmg is equal to 272.0 newtons. And the normal force is the exact same because those are always balanced. 272.0 newtons. And this time she's pulling to the left. So our tension force, Ft, is equal to 194.0 newtons. And our frictional force, which is less than the tension force, is equal to 156.0 newtons. So let's figure out our net force, or our sum of forces in the y direction. So up force is positive, so we'll do 272.0 newtons minus gravitational force, which is equal to 0. And then the sum of forces in the x direction. So in this case, the friction force is positive because it's to the right, and the tension force is negative because it's to the left. So our net force is minus 38 newtons. So it's to the left, so it's negative 38.